This video is designed to help you with various assorted counting problems. So we'll look at some different techniques for adjusting for variations in the counting or twists in the counting. So here's a good problem. This first one is, how many distinct anagrams of the word banana are there? So first of all, a couple things to recognize. I'm asking you for distinct anagrams, and a distinct anagram means that you could tell one rearrangement of banana from another. So that's what an anagram is, of course. So this is going to require a little bit of finagling, and a lot of times with these counting problems, if you assume order matters and then extract for the overcounting, you'll get a nice clean way of doing the problem. And much like a combination problem, although this is of course not a strict combination, but it is a variation on it. So one way to do that is to pretend that banana has distinct letters. In other words, we'll call them a sub 1, n sub 1, and then a sub 2, n sub 2, and then a sub 3. And then every rearrangement would look different because you have a subscript attached to each letter. So since there are 6 letters, that means there are 6 factorial ways to rearrange these letters that would all look different. Now, what you want to do is adjust for the fact that all of the A's actually are not different and therefore would look the same. What that means is for every particular arrangement, let's say banana, you can rearrange the A's within those the 3 spots of the word banana, and that would give you still banana. So how many ways are there to rearrange those A's? Well, there are 3 factorial ways, which means that you've overcounted. There are 3 factorial duplicates of every word banana where we've rearranged the A's. So if you rearrange the A's 3 factorial times, or 3 times 2 times 1, all of those would be on the list. Now, of course, you can do a similar process for the n's, because you could also switch the n's. So for each position of the n's, you have 3 factorial ways to rearrange the A's, and then you could switch the n's and then rearrange the A's again and go through all of those, which means there's 2 factorial, or just 2, of course, ways to rearrange the n's. So this gives us a pretty clean way of counting it. Assume order matters, and then divide by the overcount. So what this means is, if you were to make a list of all of the anagrams of bananas, you would have 3 factorial over times 2 factorial, so that's 6 times 2, or 12 duplicate versions of the word banana, or ananab, or abnada, or whatever. So every one of those is going to be showing up 12 times in the list, which means the list is 12 times too long. So really what we have is 6 times 5 times 4 over 2, if we're simplifying a little bit. And then, of course, we can cancel these guys and replace that with a 2, and we're going to get 60 variations of the word banana. So that means if you made the list and they were all distinct, you'd have 60 versions of the word banana that you could, rearrangements of the letters of bananas that would spell a word, in quotes. And so, there's the answer to this problem. Let's take a look at some other different kinds of problems. Here's a substantially harder problem, but we have a couple of nice entries into how to do this. So part A, you could actually count part A case by case. So you could get 4 different cases where you'd say, since it's part A says at least 1 5 appear, then case 1 would be exactly 1 5, case 2 exactly 2 5s, case 3 exactly 3 5s, and case 4 exactly 4 5s. In other words, they're all 5s. And then you would add those numbers together. So Let's do the cases for this one, and then we'll look at a faster way to do this problem, and then we'll do a faster way for part B as well. So case 1, 1, 5. And so that would be 4 ways to choose which die is a 5. Choose the die to be a 5 times 5 to the third, which is you know, all the different ways that the other dice can be not 5s. So choose values for other 3 dice not 5s. And of course this winds up being, if you work it out, exactly 500, because it's 4 times 125. Case 2 is going to be 2 5s. Okay, and you would sort that out by choosing C42 to choose where the 5s are. And then the other 2 dice are going to be 5 squared. Choose the other 2 dice, okay, not 5 for other 2 dice. Okay, if you work this out, this turns out to be 150. Case 3 is going to be 3 5s, and of course that means it's C43. I'm not going to put the whole label under it, but you're choosing which 3 dice are going to be 5s. Alternatively, you could choose which die is not a 5, but that would be the same thing. And then the last die has 5 choices of choosing a number that isn't a 5. This winds up being 20. And then, of course, case 4 is all 5s. And there's only one way to do that. And the only way to do that is to have all of them be 5s. If you add all of these up, you're going to get 671 ways to do it. Now, alternatively, you could do this problem the following way. You can take all the different ways there are to roll the dice, which is all the different outcomes you can have. So there's 6 choices for the first die, 6 choices for the second, and so on. So this is all ways. And since we have a problem that says at least 1 5 appears, that means we could subtract off all the cases where no 5s appear. And that can be found relatively easily by doing 5 to the 4th. In other words, all the different ways no 5s appear. And that is simply saying you can choose for each die anything except 5. So you could have a 1, 2, 3, 4, or 6 for each of the dice. That means there's 5 choices for each die, so it's 5 to the 4th. If you do this calculation, you wind up also getting 671. So there's your answer for part A. Part B could be done in a very similar fashion to what we just did. You could also do case by case on part B, the cases where there's exactly 1 5 and no 6s. Exactly 2 5s and no 6s, exactly 3 5s and no 6s, etc., etc. Or you can do it all the different ways you can roll no 6s. So no 6s, always no 6s. And that's going to give you 5 to the 4th, because for each die you have a choice of 5 different numbers, not including 6, of course. And then subtract off all the ways where there's no 5s or no 6s. So that is going to be 4 to the 4th. So it's a very, very similar process to the faster way we did part A. And so this is no 6s or 5s. And if you solve this, you can fairly quickly get that this is 369, which you can also get in the case-by-case basis. Let's take a look at another problem. This one is a slightly tricky problem in the sense that you have to recognize that in a 4-digit number, in the thousands column, you are not allowed to have a 0. So you have to kind of take this one case by case, because it depends on if the thousands column is an 8. In other words, it's the 8 that you're looking for, or if it's not the 8. So let's do case 1. So case 1 is 8 is in the thousands digit. Okay, so that means in case 1 you have one choice for what you're going to put there. We've already chosen an 8. So place 8 in thousands digit. Okay. What that means is we've already used up our 8, but for every other digit we have 9 possibilities of what can go there. So this is going to give us all the different ways we could do it where the 8 is in the thousands digit and every other digit is not an 8. Not an 8. Okay. So that gives us 9 to the third, which is 729. And case 2 then is where the 8 is not in the thousands digit. So the 8 is not in thousands digit. So that means we have 3 choices for where to put the 8. So let's do it this way. Let's say 3 is choose where to put 8. Okay, and then we're going to have 8 choices now for the thousands digit. Choices for thousands digit. And the reason we have 8 choices is because we've already chosen an 8 to put somewhere else, which means we can't have 8 in the thousands digit, and of course we can't have 0 in the thousands digit. So we can have 1, 2, 3, 4, 5, 6, 7, or 9 in the thousands digit. And then we have 9 choices in each of the other remaining spots. So not an 8. We can have 1 through 7, 9, and 0. What this gives us is 1,944, and that gives us a total of 2,673 different 4-digit integers that contain exactly 1 8. Okay, let's try one more problem. So this is an interesting problem. This has a little bit similar to the at least one problem that we did at the beginning of this video, because we're asking how many ways can this woman invite a group of 1 or more of her friends. So that means she's inviting at least one friend out of her 6 friends to dinner. Obviously she isn't having a dinner group if it's only her. So that means we can do this problem as case by case, where each of the cases were specified as exactly one friend, how many ways to invite exactly one friend, and that would be, of course, choosing one of the friends out of the 6, so there'd be 6 ways. And then you can choose exactly 2 of the friends, which would be C6-2, because you're choosing 2 out of the 6, and so on. And you could do this problem case by case and then calculate each of those cases and add them all together. But there's also, and if you do that, you'll get the answer of 63. If you look at this a slightly different way, it turns out to be very useful for counting these kinds of problems, particularly when the case by case gets to be odious, if there's 20 friends or 30 friends. So there's a very clean way to do this, and that is to say every way of choosing each friend, so we'll say friend 1, friend 2, friend 3, friend 4, friend 5, and friend 6, if you think about it, what you're really doing is saying it's a decision tree where I'll make a decision on friend number 1, yes or no. And then I'll make a decision on friend number 2, yes or no. And you're going to get a tree that is based on the multiplication principle. So you have two choices for friend number 1. You can say yes or you can say no. You also have two choices for friend number 2. So what you're getting is a tree that looks like this. Friend number 1, yes, no. And then you're choosing friend number 2, yes or no, depending on whether you chose yes the first time or no the first time, and so on with this tree. Now, that means that the total paths through this tree is going to be 2 to the 6th power, and with one little clever adjustment, we can recognize that instead of, which is 64 by the way, instead of every path through that tree being okay, there's one path in that tree where you said no to every friend that isn't okay. So what this problem is 2 to the 6th minus 1 is all the paths through this tree. Once again, off of each one of these you get this, and so on. So there's 64 minus 1 paths through there, or 63 paths through there. 63 total paths with at least one friend invited. Because what we're doing is eliminating the path that has no friends invited. And so this is a quick way to count a number of problems where you need to make a decision about yes or no, or yes, no, maybe. Any way you can match a nice tree like this to your multiplication principle, that might be an easier way to count what on first glance might be a case-by-case problem. So remember we're eliminating path with no friends. Okay, so 63 is the answer to this problem, and I hope that's helped give you some ideas of some nice ways to count various problems.